review what we talked about in 6.5. So 6.5, we're talking about exponents in scientific notation, right? We started talking about exponents. So we have the definition that exponents, if a is a real number and n is a natural number, what's a natural number again? A natural number is like a counting number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Not zero and not negative numbers. So n is a natural number. A to the n power is a multiplied by itself n times, right? So knowing the definition is definitely the most important part of this, because all of these other rules that we did are just kind of shortcuts, right? They're just kind of shortcuts once you know the rule. So note a is the base and n is the exponent or the power. So we use the definition to rewrite 2 to the fourth is 2 times 2 times 2 times 2. It's 2 times itself, right? It's the base times itself that many times. We all know this, right? So then we did some examples, and the important example that we noticed was right here, right? Negative 2 to the fourth, the exponent only applies to what it touches. So negative 2 to the fourth, that exponent applies to negative 2 because it's touching those parentheses. So it's applied to everything inside of those parentheses. Here I have negative 2 to the fourth. This exponent 4 is only touching the 2. It's not touching the negative. Right? So that was the important distinction between these two problems. And that's the most common mistake. Okay? So then after we did the definition, we did some rules. We had the product rule, x to the m times x to the m, n equals x to the m plus n. And we said, hey, if we can't remember that rule, write down what you know, right? X squared is x times x. X to the third is x times x times x. This is x to the fifth, right? Because it's x times itself 5 times. So this rule is handy to know, but if you can get back to it from the definition, then it's not something new you need to memorize, right? It's definitely a handy shortcut, but it's not necessarily something you need to memorize. Same thing with the subtraction rule and the power rule, right? X to the third squared. Well, if I have something squared, it's that thing times itself twice, right? So you can come up with those rules if you know the definition of the exponents. Then we had some more rules. Anything to the 0 power is 1. If you have a negative exponent in the numerator or denominator, you switch its place and make the exponent positive. So then we did some examples. All right. So that's all that we're doing from the exponents. Now we're going to talk about scientific notation. Okay, so scientific notation is used in a lot of sciences. So let's do a definition. A number is written in scientific notation if it is of the form a times 10 to the p, where 1 is less than or equal to a is less than or equal to 10, and n is an integer. What's an integer again? What? Negative whole number, positive whole number, 0. So A has to be a number between 0 and 1, or between 1 and 10, right? No, this should be less than 10. Sorry. So less than or equal, 1 is less than or equal to A, and A is less than 10. So scientific notation is used in a lot of the sciences, right? Like, if we're there, you know, there are huge measurements, like with distance, with, I don't know, some biology stuff, right, where things are in scientific notation. Like, if you're talking about distance to the moon, distance to Saturn, right, that's huge. So then we start to talk about that in scientific notation. So we don't need to write 10 zeros, right? That's where, so it's an easier organization of data, and it's less writing, and therefore less computation, like if you're putting it in a computer. So that's where like log and exponential functions come from, because with some of those things you're keeping track of a lot smaller numbers than, or a lot less data. So it's very beneficial if you're talking about crazy measurements. So let's talk about the rules for converting. Okay. So 1, we have if a number is very large. So we have a huge number. The first step, so I'm going to call this Roman numeral 1, and then the first step is to move the decimal place to the left until the number is like this, right? We need the number that's to the left of the decimal to be between 0 and 9. Okay? So that's the first step. The second step so multiply that number by 10 raised to the power of whatever so we're raising it to the power of however many places we moved it, right? That's what we're doing. Okay. Step 2, if x is very small, instead of moving it to the left, we're moving it to the right. And it's the exact same stuff, right? This is a positive, and if we have a small number, it's a negative. So I'm going to rewrite all of that for if x is very small. Number 1 is still the same. We move the decimal point, but we move it to the right. So we move the decimal to the right until the number to the left of the decimal is between 1 and 9. The second step is we're going to multiply by 10 to the number of decimal places we move, but it's a negative because we moved it to the right. So this is going to be a negative. We're raising it to a negative the number of decimal places we move the decimal point. So this is a whole lot of words written out for, I think, a very simple concept. So let's do some examples. So I have write in scientific notation. Okay, so this is a large number, right? So we're moving the decimal point. The decimal point is here. We're going to move it 1, 2, 3, 4, 5 places. So I'm multiplying by x, 10 to the 5th, I'm sorry. I'm multiplying by 10 to the 5th. But then what does my number become? 7.0866 times 10 to the 5th. So the number to the left of the decimal needs to be between 1 and 9, right? So that's the first goal. Keep moving the decimal point until you get this number to the left of the decimal to be between 1 and 9. Then you multiply by the number of times you move the decimal. Okay? So just like commas are important when you're doing math, right? You do a comma after you have 3 zeros. The decimal point is also important. So what do you guys think? So I have 1.2 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the 9. Yes. That's like the definition. So that's how it needs to look. Like if I had 12 times 10 to the 8th, though the number is equivalent, it wouldn't be in scientific notation. It wouldn't quite be there. Okay, let's do 0. Okay, so my number is very small. I need to move my decimal point to the right. So let's start with, what's my number? My number is going to be 3.92, right? 3.92 times 10 to the, I see everyone squinting to see exactly how many zeros there are. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm moving it to the right because it's a very small number, so this needs to be a negative exponent. Right? The bigger numbers are a little easier to count with all the commas. What do you guys think? What's my number?
Negative 3.2.
Why negative? So the negative has to do with the exponent, not the number. Right? If I move it to the left or to the right, that determines the sign of my exponent. But my number, I need to move my decimal point over until the number to the left of the decimal is between 1 and 9, right? So my number should be 3.2 times 10 to the, well, it has to be negative because I'm moving it to the right. I'm moving it to the negative 1. All these zeros don't matter. I put those zeros there to mess with you guys. Right? But these zeros don't matter. Those zeros are not necessary. It's to make sure that we know how we're doing it. So how do you guys feel about this? So the only thing you really need to make sure is that your number is between 0 and 1, and then you have your decimal and your other junk. And then times 10 to however many places you're moving your decimal place over. Positive is for the big numbers, and negative exponent is for smaller numbers. Josh?
So if you have the 0 far to the left, it will be negative 1. So all the other zeros don't matter.
These zeros don't matter.
Because that 0 to the left.
Because this is my decimal point. Right? That's like if I wanted to write, like, 1,000 as 00100. It's really a waste of ink, right? I don't need those other zeros. It's implied. So, but I was just trying to make sure that we know our A has to be like this, and then that's our number. All right. So then I think we can obviously convert from the right-hand side to the left-hand side, right? We don't need to do examples like that, do we? We'll just do one, just to make sure. I have 4.32 times 10 to the 4th. Okay, so everybody write that as a number. So the number is positive, so I need to move my number to my decimal place to the right. So I have 1, 2, 3, 4. So how many zeros do I need? 2. It's moving the decimal place over. It's not telling you how many zeros to add, right? So maybe I should have gone. You just need to fill in however many zeros you need. All right, let's do one more then. So I have a negative exponent. I'm moving my decimal place to the left, right? So I'm going to put 3, 8, 2, 4, 5. And now I'm going to say this is where my decimal place starts. I need to move it over 6 places, right? 1, 2, 3, 4, 5, 6. And now I'm going to fill in the zeros. Okay? So you should have 2, 4, 5 zeros. Are we good? Okay. So an easy way for me to remember this is, obviously you have to remember that your first number in scientific notation has to be between 1 and 9, right? Once you remember that, I just remember rules of exponents. If I have a positive exponent, I leave it alone. But if I have a negative exponent, remember that brings it down to the denominator. Right, there's this rule. If I have a negative exponent, that brings it down to the denominator, and that makes it smaller, right? If you have a fraction and the number in the denominator is big, that makes it a smaller fraction. So if you just remember that the negative exponent is smaller, that's how I remember this without having to feel like I'm learning something new. Okay, so let's do a couple more examples. So now we'll say multiply. I have 3 times 10 squared times 4 times 10 to the 5th. Okay, so multiply these and keep them in scientific notation. Okay? So how do I do this? Well, I'm going to multiply my numbers together, and then I'm going to use rules of exponents on my 10. So I can rewrite this as 3 times 4 times 10 squared times 10 to the 5th. Okay? So 3 times 4 is what? 12 times 10 squared times 10 to the 5th. I'm using my rules of exponents. What do I do with those exponents? Add them. Good. So this is to the 7th. Is that my final answer? Some people are saying yes. Some people are saying no. Who says no? Who says yes? Why? Now nobody's saying anything. Josh says no. I agree with Josh. Sue can tell me the reason. You need to convert it. What do you think? So it's not that there's no decimal, right? Because here's the decimal. Good. So this is not scientific notation, right? The number to the left of the decimal is not between 1 and 9. So I need to move my decimal place over once. So this equals 1.2 times 10 to the what power? Well, I moved it to the left. Eighth. Good. When I move it to the left, when I have a bigger number, then that increases the power. Okay, so we're still going to multiply 1.2 times 10 to the negative third times 2 times 10 to the negative, so let's do 10 to the fourth. Okay, so I'm going to change the order so I can use my rules of exponents, okay? So I have 1.2 times 2 times 10 to the negative 3 times 10 to the fourth. So what's 1.2 times 2? I feel like we need to do jumping jacks at intermittent. We have to have an intermission to do a little wake up exercise.
Let's go outside and do that.
Go outside. It's cold.
That's good.
I don't want to do that.
That's got
All right, what's 1.2 times 2? 2.4. And then using rules of exponents, 10 to the negative third times 10 to the negative fourth is what? Good, 10 to the 1. I'm adding these exponents. Negative 3 plus 4 is 1. Okay, so am I finished? Yes, because I have 2 to the left of the decimal. That's between 1 and 9, so I'm done. Let's do another example. I have 8 times 10 to the 6. That's an 8. Sometimes the most challenging thing is writing and speaking at the same time. I always make written mistakes. Okay. So I'm dividing these numbers that are in scientific notation, right? So I divide my like terms, right? I'm going to divide my number, and then I'm going to divide my 10 to the power. So I think you guys can do this, yeah? So 8 divided by 2 is 4, times 10 to the 6 divided by 10 to the 4th. I'm subtracting those powers, right?
2.
So it's 10 to the 2. Is this in scientific notation? Yes.
Yes.
Because here's my decimal. The number to the left of the decimal is between 1 and 9. So I'm done. Okay? Okay, let's do 1.9 times 10 to the 8th over 3.22 times 10 to the 12th. Well, I'm going to divide my numbers. 1.9 divided by 3.22 is what? I got 0.59. Is that good? Austin?
Yeah.
Good? Okay. Times 10 to the, I need to use my rules of exponents, right? 4, negative 4, I'm hearing both. Negative 4. 8 minus 12 is negative 4. Okay, am I finished? Yes, no. Isaiah, why no? Good, the number to the left of the decimal is not between 1 and 9. So I have 5.9 times 10 to the what power? Negative 5. You guys agree? Good. Okay, so that's all of the scientific notation stuff. We can combine multiplying and dividing, right? It's just rules of exponents. Do you want to do one that combines multiplying and dividing? Yes? So let's say we have 5.44 times 10 to the 8th times 2.1 times 10 to the negative 3 over 3.4 times 10 to the 6th. So let's look at the numerator first. Who's got a calculator? 5.44 times 2.1, right? Who are we going to help with? 11.42. Thank you, Austin. Times 10. So I have 10 to the 8th and 10 to the 3rd. So I'm multiplying those. Rules of exponents say I need to add them, right? Okay, so this is a 10 to the what power? Fifth. 8 minus 3 is 5. So then I'm not gonna put that in scientific notation yet, right? It's clearly not in scientific notation, but let's wait till the end so we're not doing multiple scientific notations. So divide by 3.4 times 10 to the 6th. Okay, what's 11.42 divided by 3.4? 3.36 times 10 to the what power? Good, -1. So see how I didn't need to convert that? You would have added an additional step, and then you would have had to undo it here at the end. So this is in scientific notation. The number to the left of the decimal is between 1 and 9, right? Mm-hmm. So we're good. Okay, so we're good with this? Yep.